Hi everyone, I'm Kathy, a math grad student from Dartmouth College. In this video, I'll be talking about pentascam for permutations. This is a joint work with my advisor Sergey Lizolde. First of all, what's pentascam? In pentascam, player A selects a binary word of length k greater than or equal to 3. Then player B selects another binary word of the same length. A fair coin is tossed rapidly to determine a random binary word until one of the player's words appears as a consecutive subword, making that player the winner. For example, say player A chooses HHH, player B chooses THH, and the outcome of the coin tossing is as written here. Since THH shows up before HHH, player B wins. It's known that for any word picked up by player A, player B can always has a winning strategy. This property makes pentascam a non-transitive game, meaning that the directed graph of beta relations among words has cycles. The exact odd can be computed using Conway's algorithm. In this video, we consider the analog of pentascam for permutations instead of words. So instead of binary words, player A selects a permutation of length k greater than or equal to 3. Then player B selects another permutation of the same length. Then random numbers are generated uniformly randomly until relative order of the lost k numbers is given by one of the player's permutation, making that player the winner. Say player A chooses 1 to 3, player B chooses 2, 1, 3. We generate numbers uniformly randomly from 0 to 1. We can see that the first two numbers form the 2, 1. With the third number, we have a 3, 1, 2, and then a 4, 1, 3, 2, and then a 5, 2, 4, 3, 1. With the sixth number, we have 3, 1, 4 at the end, which forms a 2, 1, 3, so player B wins. Formally speaking, let X be a sequence of identical, independent, distributed, continuous random variables. A consecutive occurrence of a permutation sigma, sometimes we call a pattern, is a subsequence whose entries are in the same relative order as sigma. After player A chooses a permutation sigma and player B chooses a permutation tau, the random variables are drawn onto consecutive occurrence of sigma or tau appears, which determines the winner. We're curious about if there's also a winning strategy for the second player in pentascam for permutations, and what other properties it has. The first result we have is the expected time to see the first occurrence of a pattern. For pattern sigma of length k, let T sub sigma to be the smallest j, such that X contains an occurrence of sigma. Let alpha sub n of sigma be the number of permutations of length n that avoid the pattern sigma, and denote the corresponding exponential generating function by p sub sigma of c. Then surprisingly, the expectation et sub sigma is simply p sub sigma when z equals to 1. We then talk about the probability to see one pattern before another. Say we have two permutations sigma and tau, denoted by PR of sigma precedes tau, the probability that sigma show up before tau in X. We define f sub sigma to tau as the number of further steps to see the pattern tau after the first occurrence of sigma, assuming that sigma occurs before tau in X. Then we have the following formula for this probability. The disadvantage for this formula is that we haven't found a general formula for EF sub, say, sigma to tau for any general sigma and tau. So we need another more practical formula here, so we can compute some probabilities. For the same sigma and tau of length k, let AV sub n to the sigma of sigma and tau to be the set of permutations in Sn that end with sigma and avoid both sigma and tau elsewhere. Then the probability that sigma shows up before tau can be computed by summing up all n greater than or equal to k, the size of this set divided by n factorial. Using this formula, we're able to generate a table of patterns of length 3. So for this number here, this represents that with probability 0.412, we can see 1 to 3 before 2, 1, 3. And observe that since either sigma or tau will win, so we don't need to worry about the lower left corner of this table because it's simply 1 minus the corner. Also, sorry, the probability that sigma shows up before tau is the same as the complement of sigma shows before the complement of tau, so we don't need to worry about the right lower corner. As a result of the previous two observations, we know that the probability that sigma shows up before sigma bar, which is the complement of sigma, is 0.5. So we only need to worry about the rest 6 probabilities here. Just to remind you that we'll use this formula to compute the 6 probabilities. So all we care is actually the size of the set of permutations that ends with sigma and avoid both sigma and tau elsewhere. So to see why it's a tie between 1, 2, 3 and 1, 3, 2, we have a general formula that if we have an increasing pattern and an almost increasing pattern except for the I here, then the probability that I k precede rho k is half, and the bijection is simply move I to the end and move it back. So the number of permutations that end with 1, 2, 3 and avoid both 1, 2, 3 and 1, 3, 2 is the same as the permutations that end with 1, 3, 2 and avoid both 1, 2, 3 and 1, 3, 2 elsewhere. So the case 1, 2, 3 and 1, 3, 2 is simply when I equals to 2. The second probability we're talking about is the probability that 1, 3, 2 will show up before 2, 3, 1. It can also be computed using bijection. Again, we want to know the number of permutations that end with 1, 3, 2 and avoid both 1, 3, 2 and 2, 3, 1 elsewhere, which is the same as the permutations that end with 1, 2, 3 with at most 1 Bailey and no peak. The bijection is, again, by moving this k minus 1 to the right and then move it back. So the number of permutations that end with 1, 3, 2 with at most 1 value and no peak can be computed using sum up all I from 0 to n minus 3 and minus 1 chooses I. So it's about 0.476. Now for the probability that 1, 2, 3 will show up before 2, 1, 3, we first compute the number of permutations that end with 3, 1, 2 and avoid both 1, 2, 3 and 2, 1, 3. Which is given by a recursive form. Then using this number, we're able to compute the desired number, which is the number of permutations that end with 1, 2, 3 and avoid both 1, 2, 3 and 2, 1, 3 elsewhere. So with this recursive form, if we let bx and cx be the corresponding exponential generating functions, then the probability is simply C of 1, which is about 0.412. The red 3 probabilities can be computed using recurrence, and it's actually more and more complicated. So we will skip the details here. So you can see the slides if you're interested. But one thing we would like to mention is we do have a conjecture that assume player A picks sigma, then one of the winning strategies for player B will be to pick sigma k, so move the last digit to the front, and then the following is of the symmetric order of sigma 1 to sigma k. This is true for pattern 3 and 4, and we're hoping to prove it for any general k. We also have Markov-Chain variation for Penny-Scan for permutations. So instead of having independent identical distributed random variables and considering their relative order, at each step, we generate a permutation from the previous one by deleting the first element and inserting an element at the end, which takes each of the k possible values with equal probability. Say we start with 1, 3, 2 with probability 1, 6. Sorry, we delete 1, then the remaining 3, 2 forms a 2, 1. Now with probability 1/3, we will add a 1 at the end. With probability 1/3, we will add a 2 at the end and form a 312. And with another probability 1/3, we will add a 3 at the end, forms a 213. So starting from 132, we have 3 other possibilities: 312, 321, 312, and 213 to show up at the next step, and they all have probability 1/3. And it's impossible to go from 123 to, let's say, 123. Sorry, it's impossible to go from 132 to 123 in this case. So far we have an algorithm to compute, given the permutation of any length, the expected time to see this permutation for the first time. And given 2 permutations of the same length, the probability that one shows up before another. We also have conditions for 2 patterns to be equivalent to each other, and a condition for 2 patterns to be tied. We're still working on discovering more properties for Markov variation. Here's a list of references. Thank you for your watching.